one more slide about implication because it's so special. And for implication, I would like to go over alternative and equivalent ways to really expressing P implies Q. So there are different ways actually of saying P implies Q, but they really meant the same thing. You might hear other mathematicians or engineers actually talk about the alternative ways. Let's now go over them one by one. Let's see the first one. So we can say Q if P. Intuitively, that means Q will be true if P is true. So Q is true if P is true. Exactly consistent between the two notions. And one thing I would like to know, this is rather a straightforward one. But remember, we spoke about proving the equivalence using if and only if. So this if over here is just the part 1. And we talked about part 2, only if as well. Well, that's this one over here. Okay, so be very careful about the order. Over here, you can say for if and also only if over here, right? To really refer to the saying P implies Q implication over here, you can see the order over here is actually different, right? One is about Q, so P implies Q is the same as Q if P, as we explained. However, whenever you want to say if only if, you don't really say Q only if P, which means something completely different, right? So when you say P only if Q, that actually means semantically P implies Q. Just be careful about the order. The order does matter. So that's why it's so important for you to understand what only if, what each one of the alternative really means. Let's try to understand that. Okay. I'll also do some illustration for you just to make it clearer. So when we say P only if Q, so this will be the rationale behind by calling this. Okay, P only if Q goes like this. We want to say if P, we know that P is already true. The only way to actually make the entire proposition true, which is this one here, right? If we know that P is already true, how can we be sure the entire implication or the entire contract is actually true, which is not breached? Right? In that case, the only choice we have is Q is true. So that's why we say only if Q is true. That's kind of the story. Let me just give you some illustration over here. Let's now, first of all, get ready the truth table for implication over here. Okay, and then what we want to discuss is about the one alternative to P implies Q. Let me highlight it. P implies Q. That's what we're considering. And we're saying that semantically speaking, it would be equivalent to say P only if Q. So P only if Q. Okay, so only if is what we are learning right now. Okay, and this really says this really means literally the following. Okay, P holds, then the only way for this implication to hold, to be true, is if Q holds over here. Okay, I will highlight the corresponding rows in the truth table, but before that, you can see here we got the only way is if Q actually holds. That's why we got only if over here, right? So which two rows are we talking about? We are basically talking about these two rows. If P is already true, if P is already true, if P is already true, the only way for the final result to be true is when Q is actually true, right? And you can see this row over here is actually not selected because when P is actually true but Q is actually false, in that case, implication will actually be false. We explain why this will be analogous to breaching the contract, right? All right, so that's about the only if over here. Again, when P is actually true, the only way for P implies Q to be true is when Q is true. That's why we got the only if convention over here. All right. Hopefully that's clear to you. Let's now go back. And if there's something new to you which you didn't learn before, or you didn't understand fully before, now you learn something new. That's good. All right. So now let's have a note over here. What I said before, if you want to prove P is equivalent to Q, how can we prove it? We want to prove P if and only if Q. So what do we really mean by P if and only if Q? So now you will be ready to actually take a look at these two, right? By applying the if and only if that we actually have learned already, and then try to put P and Q in the right order. Okay, the idea is very simple. Okay, basically, if you want to prove P if and only if Q, the symbol here tells you two things. You want to prove that P implies Q, go from left to right, and also you want to prove Q implies P, right? So let me show you the two. Okay, you can see we want to prove that P implies Q, and also we want to prove Q implies P, right? If you apply the two things that we just talked about, you can actually try to convince yourself. I'm gonna point out. I will just point out that to you. Okay, so P implies Q. We know that alternatively we can say P only if Q, right? So if P is already true, the only way for implication to be true is when Q is true. So that's why we say P only if Q, right? So this is one direction. So what about the other direction? Q implies P. In that case, we can say P if Q. P if Q, we are saying that if Q is actually true, then P is true, right? So if Q is actually true, then P is true. So in order to prove these two implications, by proving these two implications, we will be able to prove if and only if and also equivalence. So that's why usually we say P if and only if Q. So P if and only if and Q over here, right? You can see the order here is a little bit tricky, but you have to understand the alternative and also their rationale very well in order to grasp and also to use the ideas naturally, right? I'll leave that reflection maybe to you to think about it. But if you got any trouble, let me know. Okay, let's move on. The third alternative, which would be P is sufficient for Q. This is rather simple. We're saying that in order for Q to be true, it would be sufficient for P to be true, right? Because P implies Q. Okay, for Q to be true, it's sufficient to prove that P being true. Okay, because otherwise implication will be false. Okay, Q is necessary for P. Okay, so Q this one over here, it's more like a necessary condition, right? So Q is necessary for P. So it will be similar argument to P only if Q, right? So here we want to say if we know that P is actually true, right? P is already true. And then the only way for the implication to be true is when Q is also true. In that case, Q being true is necessary, right? That's something I would like to just go over with you. Okay, let me switch back to this. Similar. Okay. Hey, let me use a different color. So we want to say Q. Let me just say exactly the wordings I got is necessary. For P. Very similar idea. We want to say if P holds, then it is necessary for Q to hold such that the implication actually will hold, right? So over here you will see what we are studying right now is the necessary for. All right, it's a similar argument pattern as we did before. Okay, the final one is Q unless not P. Okay, this one looks a little bit tricky, but I will help you a little bit with that. So Q unless not P. So this is the hint question for you. When is P implies Q true? Okay, that's a very good question here. Let's now switch to iPad and take a look. Okay, let me get a diagram ready over here. Okay, when is P implies Q actually true? Okay, well, by looking at the truth table, let's now highlight the corresponding row. Let me put it in green. Okay, actually, let me use orange. This is true, and this is true, right? This is also true. So we're talking about the cases where the implication is actually true, right? True here, and also true here. But the cause of being true is slightly different. There are two reasons for that. It's either because P is true and Q is true. So this is the case where the promised terms are met and also the duties are fulfilled, right? So this is can be two reasons. Number one, both P and Q actually hold. Okay, but number two over here, okay, in the case where P is simply false, meaning that the promised terms are simply not met, then we said before, doesn't matter if you fulfill the duties or not, the contract will simply not be breached because it's simply invalid, right? So number two, which is something that you want to make sure you actually review, maybe something you may have forgotten. Okay, so number two is P actually does not hold. Okay, so these are the two conditions under which P implies Q will be true. Okay, that's a hint question for you. Okay, let's now go back over there. So Q unless not P over here really try to characterize those three rows that we actually highlights. How? Let's now go back to the rows highlights over here. So Q unless not P. Let me write it down. So Q unless not P. Okay, thinking this way, when is P implies Q true? It's either Q unless not P. So that will be the whole sentence to actually consider. Okay, so what do we mean by Q? In the case of Q, that means when Q is actually true. So in the rows where Q is actually true, where are they? So let's now highlight them. So this will be the row, true, right? And also true over here. These are the only two rows where Q is actually true, right? Over here. In that case, when Q is actually true, the corresponding value for P implies Q is simply just true, right? Regardless of P over here. But there's another possibility. That's why we got unless. Q is true unless P is already false, meaning that the promised terms are actually not met. So what about not P? Okay, let me just be a little bit more careful here. So Q is what I just highlighted, and let's also highlight not P. So not P is when the promised terms are actually not met over here. Okay, so you can see only these two rows actually got the P being false. Their corresponding values are simply just true for implication, regardless of the Q, right? So this one is a little bit visual over here to really fully understand. Let me say it again. To really understand Q unless not P, you want to consider its equivalence P implies Q over here. So ask yourself the question, when is P implies Q true? And visually speaking, it's either when this part over here is actually true, unless you know that the P, it's either when the Q over here is actually true, unless you know that the P over here is actually false, right? That's actually how I would understand the unless. Of course, it depends. This is just one way of saying the implication. If you don't feel comfortable about this to say it verbally, that's okay. But at least you should really understand what's going on over here. But I already explained to you the rationale behind why it is called this way. Okay. Okay, so that's about the last one. I also got some additional details over here, which I already mentioned. You can also refer to them. All right. So that's about the discussion I would like to brush up with you about the implication, right? We talk about its intuition, and also we talk about its alternative sayings, okay? Make sure you review them. Right, so let's move on to propositional logic. So given an implication, actually one more thing about implication is so important, right? Given P implies Q, we say that by negating both the antecedents and also the consequence, we said it's the inverse of the implication, right? By negating both antecedent and consequence. What we can have a converse, in that case, we simply switch Q and P, right, into here. Switch the order. And also we got something called contrapositive, meaning that not only that we want to switch the order to Q and P, but also we're going to negate both of them. That's called a contrapositive. And I'm sure you learned about a theorem before. P implies Q is equivalent to not Q implies not P. And that theorem is called exactly contrapositive, right? That's something you should know. But on the other hand, P implies Q is not equivalent to Q implies P. They are not equivalents, okay? In general. And also, P implies Q is also not equivalent to not P implies not Q in general. But P implies Q is always equivalent to not Q implies not P. If you want to prove it, you can definitely use a truth table to prove it. But I'm going to leave that to you if you want to convince yourself. But these are the three terminology, the terms you actually want to make sure you understand and also know. All right, so let's see some easy axiom. I cannot exhaustively list all the axioms or theorems that you're supposed to know, but I will just give you some examples. You can definitely go back to your earlier math course to actually see what's available there. Okay, so what would be the definition for P implies Q? It's simply not P or Q, right? This one actually looks very familiar, don't you think? Okay, let's take a look. Okay, over here I can definitely draw some connection for you. Okay, over here we'd say P implies Q is equivalent to not P or Q. It's a very similar rationale as Q unless not P, right? In order for P implies Q to be true, it's either when the antecedent is actually false or when the consequence is actually true. Over here, right? Not P or Q. Exactly, right? So you can also link to this particular diagram. So that's why I'm putting these two at the same page over here, just for you to actually see, right? Next one is a theorem. So it's called identity of implication. So if you say true implies P, it will just be equivalent to P. Thinking this way, if I know that the antecedent is already true, in that case, the only way for the implication to be true is when P is actually true, right? That's the equivalent to just P itself being true, right? And zero of implication. If I know that this part over here, the antecedent is already false, in that case the promised terms are actually not met. In that case, it doesn't matter what P is. P can be true, can be false, but the eventual result for implication will just be true, meaning that the contract is simply invalid, so it cannot be breached. Okay. All right, so axiom about De Morgan, it's very, very common. Okay, so you can distribute the negation over to conjunction. In that case, you would say not P or not Q, right? It's gonna negate both the operands not P and not Q, and also switch and we'll switch from conjunction to disjunction. Similarly, you can distribute the negation over disjunction. In that case, we'll move to conjunction, right? That's something you also learned before about De Morgan. All right, double negation, very straightforward. I don't need to bother you too much. I'm listing them just for your reference. Contrapositive, right? So this is called the contrapositive of P implies Q, and they happen to be equivalents. Okay, this is the contrapositive of this over here. I'm not sure why it's highlighting both over here. Okay, never mind. This way, okay, this way here, and then they're equivalents. All right, so these are just some example axioms and theorems I want you to just at least understand. But if as more theorems and axioms are needed for our lecture purpose, I'll definitely add them to the slides and also mention them to you. All right. All right, so that's about the propositional logic that I'd like to talk about. And next one, we're going to talk about predicate logic.